In this slidecast, we'll cover bubble sort. Bubble sort is also a quadratic sort. It compares adjacent array elements and exchanges their values if they're out of order. And smaller values bubble up to the top of the array and larger values sink to the bottom, so hence the name. Here's an example array that we'll sort using the bubble sort. We'll follow the pseudocode. We first, for each pair of adjacent array elements, if the values in the pair are out of order, then we'll exchange the values. So we want the array sorted in ascending order. So the first two values, we'll go ahead and swap them. Then we'll go to the next two values. They're in order. We'll go consider the next two values. They're also in order. And finally, we'll consider 3 and 4. They're out of order, so we'll swap them. Now at this point, once we're done with pass 1, the last item is guaranteed to be in the correct position. It's the largest item. So we don't have to test it again. So we've colored it blue to indicate that it's in sorted order, and now we'll go back and we'll repeat the process again. So we go back for pass 2. The first two values are in sorted order. The next are in sorted order. These are not in order, so we'll swap them. And now once again, the 75 and 83 are in their sorted positions. So we'll go back to the beginning. On pass 3, the first two items are in order. The next two items are not. We'll swap them, and now the 60 is in order. Now we're just left with the first two items. For pass 4, we'll compare them and we'll swap them again. So you notice 27 started out at the bottom. So on every pass we had to swap it to an earlier position. And now the array is in sorted order. So where n is the length of the array, after the completion of n-1 passes, then the array is sorted. Now sometimes an array will be sorted before n-1 passes, so we could detect that if we make no exchanges during any of the passes, we can stop because the array is sorted. And the algorithm can be modified to detect exchanges. We'll do that next. So here's a refinement. We initialize the exchanges to false, and for each pair of adjacent array elements, if they're out of order, then we exchange them, and then we'll set exchanges to true. So that way we'll know whether an exchange occurred during one of the passes. Now in analysis of this sort, the number of comparisons and exchanges is represented by this series. We start with n-1 comparisons, then n-2, and so forth, until the last pass we just make 1. So the worst case performance is that the number of comparisons is order n squared, and the number of exchanges is order n squared. Now compared to selection sort, it had order n squared comparisons and order n exchanges, so bubble sort usually performs worse. Now if the array is sorted early, the later comparisons exchanges are not performed and performance is improved. So the best case occurs when the array is sorted already. So one pass is required, order n comparisons. No exchanges are required, they'd be order 1 exchanges. So bubble sort works well on arrays that are nearly sorted, and it works worst on inverted arrays, where all the elements are in reverse sorted order. Here's some C++ code for a bubble sort. So here's our bubble sort routine. It takes as input a random access iterator first, and then last is an iterator that represents one past the end of the sequence. And here's our do while loop. Basically, the elements after position last minus pass are in place. And here we're using the exchanges Boolean value to recognize whether an exchange occurred. And we'll continue sorting as long as an exchange has occurred during a pass. When we're done with this do while loop, the array will be sorted. And that's the end of this slidecast.